Now for number one there, what percent of full charge is a 150 microfarad capacitor connected in series with a 3 kilo ohm resistor at 30 milliseconds after closing the switch? Now you notice I didn't give you a voltage, did I? Voltage doesn't matter, does it? Because remember, it's the time constant that matters. The percentage of charge that builds in a given period of time is the same regardless of what the voltage is. It depends on the capacitance and the resistance. So technically that percentage of charge can actually be found without having the initial voltage. It is just that constant of 1 minus e, the power of negative t over tau. Remember, tau is RC. So for this problem, it's 1 minus e to the x. We're going to put in negative, our time is 30 milliseconds, so 0.03, divided by, we're going to put this in parentheses, r is 3 kilo, so that's 3,000, times 150 micro is 0.00015. Close that parentheses. For most of you, you'd have to put a parentheses in front of the negative and then a second parentheses at the end because you don't have the raised exponents if you're not dealing with a graphing calculator. You get 0.06449. That is saying that is basically, if you move that decimal point to make it a percent, that's 6.45%. So in 30 milliseconds, it charges 6.45%. How could we make that charge faster? Less resistance. Number two, this is a little more conventional. You have a 50-volt circuit with a 4.5 kilo ohm resistor. 5 millihenry inductor is closed. And the circuit is the current is increasing. Find the current after 8 milliseconds. Well, our increasing current in an inductor is what formula? One minus e to the negative t over tau. And remember, tau is perfect, L over R. So we've got to plug this in. That's going to be 50 over 4,500 times 1 minus e to the negative 0.008 divided by parentheses 0.005 divided by 4,500. Close and close and close. So 50 divided by 4,500 times parentheses 1 minus second e to the x. Should again, most of your calculators have to put parentheses negative 0.008 divided by parentheses 0.005 divided by 4,500. Close them and close them again. Arrow out and close them again. You get 0.011. So that would be indicating the current would be 11.1 milliamps. Questions? Okay. Do you have any questions after homework that you want me to go over?
Yeah.
Which ones?
When I got to
Page 47?
there's kind of worksheets. I couldn't figure them out because it was asking for points for 1, 2, 3, 4.
Gotcha.
It was trying to get us to go to a figure, and I didn't know if there was stuff on the figure I was supposed to.
It's just trying to make a graph. Oh, figure 24.3 is not in this packet. That's why that one doesn't work.
Yeah,
This
so
page is missing.
I was looking through that.
Actually, figure 24.3 is on the previous page, or page 42. See if you see that figure here. Was it giving you position 1 is just closed. Oh, gotcha. Position 1 and 2, I'm not seeing 3 and 4. Oh, 1, 2, 3, and 4 time constants. Okay. So really all this is, the classical way of looking at these circuits is this. You have a voltage source. It goes through a resistor. And then you have your capacitor. Okay? And of course there's a switch at some point. So it's left open, and you put the switch down to close it, and it charges. So that capacitor begins to charge. So when they say position 0, 1, or 2, all they're talking about is position 1 is this type of circuit. So then the classical way of thinking about it is you close that, you charge the capacitor, then you open the switch again, and you remove the voltage source. So then you're shorting out the voltage source. So when you close the switch again, it discharges the capacitor. Well, all they did in this problem was this. Instead of having it so that you remove the voltage source, they said, we're just going to make a fancy circuit. So this circuit looks like this. So this is our switch. Position 1 is where it's connected here so that it's charging. The voltage source is now charging the capacitor. Position 2 is when the switch is here so that it's discharging the capacitor. That's all it's saying is position 1 is charging, position 2 is discharging. Then it's saying plot points for 1, 2, 3, and 4 time constants. Well, let's say we're starting out discharge, no charge on the capacitor. So we're going to position 1, so we're charging. Remember, your time constant is R times C. So let's take a look here at what they give for R time. Well, actually, we don't even need R and C here, and I'll show you why. So the voltage on the capacitor is equal to our max voltage times, this is charging, so 1 minus E to the negative T over tau, all right? If we're at 1 time constant, that means T equals 1 tau, right? Because tau is a times constant. So what that means is our voltage here is 50 volts. So that means the voltage on the capacitor is 50 times 1 minus E to the negative 1. That's 1 time constant after closing the circuit. So 50 times parentheses 1 minus E to the negative 1. Gives us 31.6. 2 time constants then would be T equals to 2 tau.
So why in the first part
Because you had to find the time constant. That's just R times C. Yep. So then our voltage then at 2 time constants will be 50 times 1 minus E to the negative 2. giving us 43.23. Three time constants, I'm just going to plug in -3 here. 47.51. Then 4 time constants, I'm going to plug in the -4. 49.08. If you plotted these points, you would end up getting curve looks something like this. As you get closer and closer to that full charge of 50 volts, because it's an upside down exponential curve is what it is. There's a percentage here. 31.6 over 50 is that 63.2%? One time constant usually is 63% charge, they say. What's left? Well, what's tricky here is now we got to look at what's left over. For the second time constant, there is 18.4 volts left to charge. That's just the difference from 31.6 to 50. And we charged, was it 11.63? That's the difference from 31.6 to 43.23. If we divide that out, we again get 63.2. So each time constant, it accumulates 63.2% of the remaining voltage to go up to max voltage. Does that make sense? And that's really what the time constant is for an RC circuit, is it's 63% is what they usually say, but it is technically 63.2% of whatever remaining voltage there is accumulates in one time constant as you're building. And the same would happen as you were discharging it, is 63.2% of the voltage would discharge in one time constant. I won't be quite that cruel to you on a test. Any other questions you want to see off the homework? That's it. That was still one of the homework questions. Okay, so this new packet that you just got is about logarithms and exponentials still, but it's specific to what's important to you guys in electronics, and that is power. I don't know when you guys have your signal testing, but most of your signal testing is done on a logarithmic scale. Your basic unit of power gain is a bell. A bell was named after, of course, Alexander Graham Bell, one of the pioneers in transmitting signals, electrical signals for communication purposes. It is simply a ratio of powers. Now, a bell is applied to a lot of things. Electronic signals, sound is measured in bells. The reason it's done in a logarithmic scale is that Alexander Graham Bell discovered that the human ear actually detects sound levels logarithmically. So what we would hear is a doubling, twice as loud is actually a logarithmic progression. So then, of course, when you convert that into electronic signals, if you want to double the sound, you got to be aware of that as you adjust those electronic signals. So the bell is a ratio of power input. That's the power that is entering a system. That's going to be capital P with a little n, to power output. The actual power that is harnessed and used by the system, so that's P out. So one bell the number of bells in a system, I should say, is equal to the log. Now, if there's no number written here, what base is that log? Base 10 of the output power to the input power. So let's say that you have a system that you are going to put in 400 milliwatts, and it puts out 500 milliwatts. So it's obviously a power gain. Now, a power gain should be positive. So we put this in, our number of bells is going to be the log of, all we have to do is make sure those units are the same, and they are. They're both milliwatts. So they can either be both watts or both milliwatts, it doesn't matter, or kilowatts for that matter. So it's 400 over 500. The milliwatts will cancel out. That is the log. 400 divided by 500 is negative, oops, I did that backwards, didn't I? Which one should go on top? 5 should be on top. It's output on top. Thank you. So log of 500 over 400 should be a positive 0.969. So 0.0969. That is bells. So that is a 0.0969 bell increase. Now, gaining 100 milliwatts, I mean, that's a 25% gain. To only gain 0.09 or 0.1 bell, basically, that's a pretty small number. A bell actually is a very, very large unit of measurement. So you guys remember the metric system, right? The standard unit, then you got deci, centi, milli. Well, a millibell was too small. You're working with numbers too large. So what they discovered was best is if they used a deci. A decibel is equal to 1/10 of a bell. Of course, a decibel, you guys are used to seeing that as 1 dB, right? So since a decibel is 1/10 of a bell, how many decibels are in a bell? 10, right? So that means the number of decibels is going to be 10 times the log of 500 over 400. So then this would make that a gain of 0.969 dB, decibels. So that's almost a 1 decibel gain. That's a little bit more reasonable unit to work with. It's not so insanely tiny, difficultly tiny to work with. So let's say we have a system that says it is a 300-watt system. It is hooked up to 120-volt power and draws 3 amps. Find its power gain or loss. Well, what is the output power? Power output is the rating of the system. It's rated as a 300-watt system. That is the power output is its rating. The power input is 120 volts times 3 amps, or 360 watts. That's the power going into the system. So in dBs, this will be 10 times the log of 300 is the 300 watts comes out, 360 goes in. Is this going to be a positive number or a negative number? Negative, because there's less coming out than there was going in. So 10 times a log of 300 divided by 360. We get a negative 0.792 dB. What do you think? Not bad? Okay, so how do you measure power in a circuit? Do you guys remember how do you measure power? Volt times amps. So now let's actually look at the physical measurement, measuring volts. Let's say here's my circuit, couple of components. How would I measure the voltage, or if I want to measure the power across this component, how would I measure the voltage across that component? Well, I just take one probe, touch it there, the other probe, touch it there, and I get the meter, it'll give me a voltage. Do I have to interrupt the circuit? No. Do I have to shut off the power in the circuit? No, I do not. What if I wanted to measure the current flowing through here? What would I have to do? I would have to turn off the circuit, unhook it, and run those wires through my meter, run the power through my meter to measure current, right? So measuring current requires us to interrupt the circuit, even for just a short period of time. How about resistance? Resistance can only be measured directly if it's a dead circuit, correct? You have to have the power shut off to measure resistance. So the only quantity that can be measured about a circuit without interrupting power is the voltage. Power is equal to voltage times current. We've seen that, or current times voltage. But we've also seen that power formula rearranged so that power is equal to the voltage squared divided by resistance, correct? Because current is equal to voltage divided by resistance. So what we're looking at here is if we're trying to find, we're going to do the input and output here on this device. If we're trying to find the power through this device here, the input power compared to the output power can be found in terms of the voltage if we can assume that the input resistance and the output resistance are reasonably close. And in a good device, input resistance and output resistance will be close to the same. Have you guys talked about input resistance and output resistance in devices yet? No? Have you guys talked about signal reflection and echo or anything like that? No? All right. Let's say this is your, I'm just going to draw it as like a pipe here. This is going into your device, right? This is going in, this is coming out. If you have, there's a resistance going into the device here. The larger that input resistance is, the more that signal is going to reflect and go back the other way. So let's say you've got a signal coming in that's strong like that. Your input resistance, what's going to happen is some of that signal is going to reflect back, some of it's going to transmit through. The higher the input resistance is, the more the signal reflects back. So the same thing is going to happen with your output resistance. So the higher that output resistance is, the more of that signal, you'll have the remaining signal, some of it's going to reflect and some of it's going to transmit through. So you keep that input resistance and output resistance as low as possible. Also, if you keep them balanced, you avoid what's called signal echo. If the input resistance and output resistance are approximately the same, what will happen is any signals that reflect here will just continue to be within the device. If they're not balanced, if one of them is larger than the other, what'll happen, of course, you've got these signals here that reflect back here. Part of them are going to reflect back, and it's going to end up going through. If it's hard to explain, but if the input and output resistance are balanced, you can capture those reflected signals in there and wipe them out. If they're not balanced, they go back and forth, and some of them leak through, and it gives that kind of an echo effect, whatever your signal is, and that's very, very bad. So on a good device, the input resistance and the output resistance are going to be pretty close to the same. So what that means in our formula here, instead of P out over P in, we can replace that with P out can be V out squared over R out, and P in can be V in squared over that input resistance. And since the input and output resistance should be equal, they divide out. So we end up with the number of decibels. Now this is dBmV. Yeah, I'll be careful. Is 10 times the log of the output voltage squared over the input voltage squared. Now, time to look at some of our math equivalencies. When I have a fraction like that, and each piece, the numerator and the denominator of the fraction are both squared, I can rewrite it as just output voltage over input voltage and square the whole thing, can I? Does that look familiar? 3 squared over 4 squared is just 3 over 4, the whole thing squared, whatever. One of our equivalencies of logs was log of x squared is equivalent to 2 times the log of x, right? Does that look familiar? So I can take this 2 here, that power of 2, and bring it out front. So instead of 10 times the log, it's 10 times 2, or 20 times the log of V out over V in. So I can compare the input and output voltages to get a gain of power. So let's say that we have input voltage, 140 millivolts. Your output voltage, 190 millivolts. How do I find my power gain? Twenty times the log of which one's V out? 190. And V in, of course, is the 140. So now the millivolts cancel out. So this will be 20 times the log 190 over 140. Now you notice I'm actually just leaving the zeros off, putting 19 over 14. The size of the numbers doesn't matter. It's the ratio of the numbers that matters there. I get 2.653 dB gain. So in your notes, I want you to try 2 problems for me. My input voltage is 50 volts. My output voltage is 40 volts. Find the power gain or loss. In the second one, my input voltage is 120 volts, an input current of 8 amps. And it is rated power output of 800 watts. Find the power gain or loss. I'll give you guys a couple minutes to do those, and we'll go over real quick. So the first one, what formula do we use? First of all, is it 20 or 10? It's 20 because we're using voltages. So 20 times the log of 40 over 50. Very good. Which is going to give us 1.938. Is that correct? That should be negative. You are correct. So it's almost a 2 decibel loss. Number 2, what's the formula? 10 or 20? That'd be 10 because we have powers. On top is going to be the 800 watts. On bottom, 120 volts times 8 amps is 960 watts. So 10 times the log of 800 over 960. I get negative 0.792 decibels. What do you think? Okay. Now I gave you a new packet, but the new homework is not from that new packet yet. This is still the old packet from before. Page 491, 1 through 61 odds. Again, I don't want you to do 32 problems. Do a couple of the first ones, skip ahead a few to the more difficult ones. Make sure you do some where they give you the straight powers, then do some where they give you voltages and currents. Take a look at a couple of the word problems. And don't forget to have your quiz done.